difference in concentration, self-diffusion, vacancy diffusion. So there's different types of diffusion. And K-targeting is just one real example of the application of diffusion in real world. So the first concept you have here in this chapter is about the rate of the diffusion, which we call flux. It's very simple. Let's see. So we have we talked about that we have two types of diffusion. One is a steady state, which is a simpler one. So it's just like a linear diffusion. As you can see here, it depends on the lengths actually, and concentration just changes linearly with the length or the position. This is example from okay, so the other thing is important in this chapter is the diffusion coefficient. Diffusion coefficient depends on temperature, right? And also we have this V naught, which is, I don't know what it's called, but this form of equation, we've already seen it in the previous chapters. I guess we have seen it in the chapter 4 as well. That's how we calculate the diffusion of coefficient for the system at different temperatures, right? So we have the D naught, which is kind of like a property of our material or system, and the temperature affects the diffusion. So that's how we calculate the diffusion coefficient at different temperatures. So it's important to know how to calculate this one. It's the same thing. So that's also important just to know the concept. So whenever we have like an exponential, well, it's very difficult to solve, right? It's difficult to work with exponential things. That's so just to make it easier to solve, we usually take a natural log, or in some cases also normal log, to make it a linear equation. And this concept applies to, I guess, many other like equations in this course. And non-steady state. So this one is also very important. So the non-steady state, so we have actually like several parameters compared to the steady state. In the steady state, just the position matters, but here we also have the time as well. So just showing the concept behind it, the non-steady state diffusion. Okay, so this is the formula. Maybe it's a little bit here, but I guess we have solved later problems and examples on this, so you should be good. And this is this error function, which you have to find from the table. And when do you have any question about this error function? I guess you should be familiar with this and how to find the value from the table. Okay, so this is also important in this chapter. And technically, yeah. So actually, like summarize the three important things here: it's a non-steady state, and steady state, diffusion, and also the diffusion coefficient. So, So it was about mechanical properties of materials, also minerals. And you learn about different things like the stiffness, the strength, the quality, and hardness. These are the different parameters when you want to explain how mechanically how materials behave. And so you have seen many like formulas in this chapter. The most simple one is stress, and the also this is like shear stress. And we go to Hooke's law, and also we have this Poisson's ratio. Let's see. Maybe you have seen like Poisson ratio in this direction. It is also important to know how Poisson ratio translates when we want to like make a connection between the strain in different directions. For example, x and z directions. And we solved some problems, examples using this concept. It's the same thing. Bulk modulus is it's another thing, just to remember this it's not that many important. And that's the definition. I'm just showing like the steps we have when we want to when we have like a tensile test, or also we want to investigate the fracture process. Of ductility, which we show it with mostly like elongation. Also, it would be stated in the form of area as well. Resilience, which means the area under the curve, only for the elastic part. Toughness is the area behind like the total curve. And true stress and strain is also important. I guess this is like a new concept. You have probably seen these other concepts before in other courses, but this should be probably new to you. And it means just like you're measuring the area at the real time. That's the difference between engineering and true stress strain, right? Yeah. So in the engineering, we have force over like a constant area, but here, area is the real-time area. And that's also how we measure the true strain. And this is like the Hooke's law for the true stress and strain. So that's how we relate these two. Well, not the Hooke's law, but that's how we relate like true stress and strain to engineering stress and strain. Oh, that's like a Hooke's law for the true stress and strain. And this is also important to know that K and N are constants related to our system, our material. Again, we have like exponential relationship here. So to make it simpler, what we do is take a natural log. Or in this case, I guess, we take just a normal log in some questions. That's the strength of probably and the hardness. So this is another parameter in explaining like mechanical behavior of materials. It's the hardness And we have different ways to measure and define the hardness. I believe you should have, I don't know if you have the slides. Yeah, so for example, one of them is rock wall hardness, granular hardness. So it's important to know like different ways of measuring the hardness. So make sure you have those like these formulas for different hardnesses in your formula sheet. And the safety design, which is simple concepts. Any question from this chapter? Okay. So. So, and also you guys have some stuff from chapter 7, as Nate mentioned. In this one, you're basically talking about dislocations, how crystal structure affects the mechanical characteristics, techniques for strengthening or increasing strength and hardness of the metals or metal alloy treatments and things like that. So like I was mentioned before, it'll mostly be example mostly calculation based. So it's also important though too to go over this stuff here, like dislocation motion, the different types of dislocations. Just to help give you more of a background when you actually do the math for these problems. So I believe, so during I believe it was last week's presentation, we were going over slip and single crystals, so definitely go over this. So here's where they were talking about the resolved shear stress. So essentially they're getting the resolved shear stress as they calculate or I should say, the applied tensile stress, shear stress components when the slip plane is oriented so that you're neither perpendicular nor parallel to the stress direction. And so to define those directions, they have lambda and phi, the angle, I should say, are defined. And that's how you come up with your resolved shear stress, which is just the force divided by the area, but you also have to take into account the angle of the slip. And here is showing the relationship between the tensile stress and the resolved shear stress. So this is an important one that you guys have to remember from homework and also from the last presentation that we did. This one here as well, the yield strength of a single crystal, that's also one that I believe you guys as well had in your homework. So basically this is just talking about yield strength as it pertains to the cross-sectional, the critical resolved shear stress. So slipping single crystal is one thing to study. Yes, we're going over strengthening mechanisms, which is grain size reduction, solid solution strengthening, and strain hardening. So in the first strengthening mechanism is to reduce the grain size, and here this is a formula for that to describe that, which is sigma yield, or basically the yield strength is equal to sigma naught, and I guess to point it out real quick, sigma naught and ky are just the material constants, so those values will be given to you so that you can actually solve the problem, and of course d is going to be your grain yield. And essentially what this slide is saying is if we reduce the grain size, the mechanical properties of your material are going to improve. Because if you have coarse grains, you're not going to have very strong material, but if you have very fine grains, your yield strength and everything increases. So this is definitely an important one to study as well for the exam.
Strength and mechanism 2, there wasn't really any questions in your homework for this, and there wasn't really to show you guys just within the textbook, but I just want to make you aware of this other strengthening mechanism, which is just solid solution strengthening. And then, yeah, so essentially you're adding impurities or substitutional atoms into your lattice, and then those extra atoms are going to improve tensile or compressive strength, essentially. And then, something like this. We did go over this one. It's in your slides. This would be a nice one to know. It wasn't particularly in the homework. I think I was just showing you guys this one because this is the other strengthening mechanism, which is strain hardening. So basically, you're strain hardening or deforming the metal by rolling it, and that deformation is what also can strengthen your metallic material as well. So the percent co-working formula would be a nice one to know, just to have on the end. It wasn't particularly in your homework, but it would be nice to have that on you guys, just in case. Here we're still talking about strain hardening and how it works. I believe there's a nice example in here. So here, so I'll go back a little bit. So here they talk about, or they begin to talk about the three annealing stages: recovery, recrystallization, and growth. So this is just pertaining to heat treating of the cold work metals to manipulate the structure in the material. So you have recovery, which they don't have any questions from homework or in the textbook about recovery. That could potentially be asked on the exam, but it's good to understand how recovery works. So basically, you're just reducing the dislocation density and annihilation of dislocations in your lattice. Recrystallization is also another one. It wasn't particularly in your homework. So recrystallization is basically the formation of more grains inside of your metallic structure. And the last one, which there was stuff in your homework about, was your granular stuff, which is basically your controlling the size of your grains or shrinking your grains through heat treatment. Or sorry, enlarging your grains through heat treatment. And let's see, yeah, so here we went over this formula. So this was something that you guys had to use for homework and also list during recitation. This is showing the empirical relationship between the average grain size and the heat treatment time. So this is a good one also too to keep in mind for you guys for the exam. And I believe this is something like these. So yeah, so basically in this chapter and kind of what I stopped and paid a little more attention to for you guys, you can expect something like that on the exam for chapter 7. And basically we were just going over how plastic deformation occurs from motion dislocations, in terms of the crystallographic structure. You just have to keep in mind the atomic distortion from dislocation motion in the slip planes and along the slip directions. Deformation of the polycrystals will change the grain shapes, and then we can use those grain shapes or try to manipulate those grain shapes to tune our material mechanically. And so, yeah, that's pretty much it for chapter 7. Did you guys have any questions on chapter 7? Is there anything you guys need to go back on to review, or maybe you guys want to see an equation real quick to write it down? Okay. And we'll just have one more chapter for you guys. Chapter
about failure. Well, generally the exam would be very similar to your homework and the recitation materials we solve here. So if you review the homework and the recitation problems, you should be good. Alright, let's get back to the fracture. So in this chapter we talked about fracture was basically just the system fails, starts with cracks, and then you can have like different mechanisms. Ductile materials follows a different process. In brittle materials, just everything shatters. I was showing the different profiles you can have for fracture. Same thing here, ductile materials, fracture like this, but brittle materials just breaks into a lot of pieces. Yeah, it's showing like the process of the fracture starts with a crack and develops. So first thing we talked about here is about the stress in a crack. Well, in a crack, the maximum stress appears on the tip of the crack. And we talked about how we can calculate that. We said we have two types of crack. They can be internal or surface cracks. And the difference is in the length of the crack. When we have a surface crack, that's how we measure the length of the crack. This A parameter, which is equal to the total length of the crack. But when we have internal crack, we actually consider half of the total length as the length of the crack. And generally, this sigma m is showing the maximum stress, which is appear here at the tip of the crack, and that's how we can measure it or calculate it. And we talk about critical stress for crack propagation. So if this stress inside the crack passes this amount, this critical stress value, then the system fails and fracture happens. And this formula is showing how we can get this critical stress. We have Young modulus. A is again like the length of the crack, and this gamma is just you can think of it as a constant, which is like a property of a material. So another thing we talked about is the fracture toughness, which is, well, the concept is very similar to critical stress. So it's another parameter we have for the fracture. Again, here we have a Y parameter, which is a constant and a property of our system. Yeah, it's talking again about the design factors that we have to be careful about. So the critical stress, the fracture toughness should not go higher than a critical value. Another example, I guess you had a similar question in the homework as well as the recitation. It just talks about testing So fatigue failure is the type of failure which happens over time and when our system, when we have like a cycling loading and our system goes over lots of cycles. So the fatigue failure, the number of cycles are very important. I don't know if you had any question. I don't think so. You're only for fatigue failure. But here, actually, the number of cycles are like the major parameter to determine if our system fractures or fails. Talks about some methods to improve the fatigue life. And creep is another important concept of this chapter. Oh, creeps. Let's see. So creep is different. Like somehow it's different from like the fracture because it happens under constant stress, and over time, that constant stress can cause different strain in our system, in our material. We talked about that usually for many of the systems or materials, usually it has 3 different steps. The primary steps, which behaves like this. The secondary step, which is the most important one, is a steady state creep, or kind of like it is a linear creep. And you can see the slope here is linear, constant. And the final step is again yeah. So the most important step is the second step, which is the linear, and we can talk about it. The primary and the last step are not linear. Very complicated, so don't talk about it in this chapter. So it talks about the effect of the temperature on the creep behavior of our material. And okay, a steady state creep. So this formula is also very important and relates the stress to that steady state creep rate. Right. And again, you have like exponential relationship. Activation energy, this K is a constant, as well as this N parameter here. So R again is a constant, and T is temperature. And so we have talked about another parameter, Larson-Miller parameter, which is connect the temperature and failure time to stress to this Larson-Miller parameter. So for this parameter, we have figures like this, which we can relate the stress to this M parameter, and from this formula, we can relate the stress to time or temperature. So that's how this Larson-Miller works. So yeah, the main concept is this Larson-Miller, this steady state creep you should know about. Fatigue behavior is not really important. And also the concepts we have here, both fracture toughness and critical stress plus the stress, the maximum stress in a crack. Those are the main concepts of this chapter. So any question about this chapter? No? So I believe we uploaded all the recitation materials up to chapter 8 on Canvas. There was one question that we couldn't solve last week, so I'm gonna show you that question first. Let's think about that for a couple of minutes, then we go to chapter 9. This degree. So think about it a couple minutes. Could you solve part 8? No one? Give you 2 more minutes. formula for the non-insidious safety, right? And since we have an exponential term in this formula, what we do is take a natural one, right? Because we cannot work with the exponential. We want to make it like a linear relationship. So if we take that natural one, we will have something like this. Okay. So we are already given QC as 272,000. Temperature is 111.23 probably. R is a gas constant. It's a general constant. You should know its value, which is 8.31. And the Earth is Joule over another. It's closer. So these are the value of the system and the material we are given. Also this one. So we are given two different situations, which is this table, and we need to find N and K2 based on these two, right? So from this equation here, we already know Q, T, and R, and we have two different values for sigma and this grip rate here. So we can make it like two equations, two unknowns, to find the K2 and N, which are our unknowns. So let's plug in these values here. So the situation one, which is this one, let's call this one, and this two. So in the situation one, sigma is 15 megapascal, and grip rate is 10 to the minus 4, right? So we'll have something like 10 to the minus 4. It's equal to K2 plus N times 15 megapascal minus QC, which was this over R times our temperature. Just be careful with the units. That's right. Well, this is megapascal when you are when you are calculating the element, you should have 15 times 10 to the power 6, right? Because Pascal is a sign. Now for the second situation, again we have something similar with different values for sigma and creep rate. So instead of 10 to the minus 4, we have 10 to the minus 6. And K2 plus N times Ln is 4.5 megapascal. The second situation. And this term is exactly the same, right? Because this is QC over RT, and these values doesn't change. So we're gonna have the same thing for this term. So as you can see, this is, when you simplify this and calculate the Ln values and this fraction, this becomes two equations, two unknowns, right? Which you can calculate, from that you can calculate N and Ln K2, which translate to K2, right? And from these two, you will have these values here. It's pretty small, but you'll have it in the slides. These are the values for N and K2. Now let's switch over to this part, so if you want to write it down. And for part B, well, it's simple now, right? Because in part B, again, we just use this formula. Just use this formula here. We want to calculate the creep rate if the sigma is 25 megapascal. So we already have Q, C, T, and R, and we calculated N and K2, and also the sigma, the stress is given as 25 megapascal, so the rest is just plugging in the numbers. So K would be, for example, 466. And we will have 25 megapascal to power N, which is 3.83 times exponential QC over R times T. And if you calculate this, you will get 2.28 times 10 to the minus 5. Is it clear, the question? Okay, so if there is no question, we can go ahead with chapter 9. Okay, so chapter 9. So chapter 9, actually one second.
like things like solid state or solubility limits and phase diagrams and all that good stuff. So I'm gonna be showing you guys stuff based on what I've seen, like the sections I've seen in your homework. So I guess this is a good, the structure of the slides also help with that. So the title of the slide is solubility limit. So if you look in your textbook as well, it'll also be labeled solubility limit. I just didn't put like the chapter and the section number behind it. But if you do like a control F on solubility limit, it should take you directly to the chapter itself. But anyways, so we'll start off with stuff about solubility limit to try and help you guys give a little background first before we jump into some problems. And then as far as the problems go, I'll do the first one for you guys to like try to walk you guys through it, and then the second one, I'll let you guys do that one. And we'll see how that goes until the end of the recitation. If there's some stuff that we still have to go over, we'll go ahead and finish that on next week Friday, and then we'll also try to finish chapter 10 too. I will say though that chapter 9, I wouldn't say it's difficult, but it's very like dense. So you guys like make sure that you're like reviewing this and making sure you're understanding, you know, how to move across the phase diagram and things like that. It's not difficult, but you gotta put time into it so that you understand what you're doing so you can answer the questions correctly. Okay, so here, one of your slides, they were speaking about, or I should say a couple of your slides, they were speaking about solubility limit. So for many alloy systems, at some specific temperature, there's a maximum concentration of solute atoms that can dissolve in a solvent to form a solid solution, and this is the definition of a solubility limit. The addition of solute in excess of this solubility limit results in the formation of another solid solution or compound that has distinctly different compositions. And one example that they use in your text is the sugar in water, which is this guy here. So in this example, they want you to consider sugar in water. Initially, you add the sugar to the water, and it creates like a sugar water solution or like a syrup form. And as you add more sugar, the solution is going to become more concentrated until you reach the solubility limit, or the solution is saturated with sugar. And so that's what you're seeing here in this diagram that I have. So if you look at the graph on the right-hand side, you'll see liquid plus solid sugar on that right-hand side of the Venn diagram, right there, separated by the solubility limit, and you also see on the left-hand side the pure, I guess, liquid solution, which is the syrup. At this point, the solution is no longer able to dissolve in the sugar if you keep adding sugar, and then at that point, the extra sugar will fall to the bottom. And so, as I was pointing out earlier, you'll see like two separate substances, which is separated by that solubility, I guess, line or that limit. And another thing to note is that your solubility limit of the sugar in the water, and also with your metals and things like that, is going to depend on temperature as well. So that's why they have temperature on the left-hand side, and on the bottom they have the composition or the weight percent of the sugar. And so that's what this other slide here was about. It was talking about how the effects of temperature, or basically the effects of temperature and composition. So how the temperature will affect the phase. And so for the first question, this one is not necessarily in your homework, but this is a nice one for us to go over just to show you guys how to approach the problems or similar problems that you're going to see like this one. So the problem reads, consider the sugar-water phase diagram in this figure 9.1, this figure here that I have up here for you guys. And they want to know how much sugar will dissolve in 1,500 grams of water at 90 degrees Celsius. I have Fahrenheit on here, but don't worry about Fahrenheit. That's just extra. We'll just deal with Celsius. And And part B is asking if the saturated liquid solution in part A is cooled to 20 degrees Celsius. Some of the sugar will precipitate out as a solid, and they want to know the composition of that saturated liquid solution in weight percent of the sugar at room temperature. And part C is they want to know how much of the solid sugar will come out of the solution upon cooling to 20 degrees Celsius. So feel free to start thinking about it and like writing about it, solving on your own. I'm gonna also begin to start another step down so I can explain this to you guys clearly, and I'll let you guys tackle the following question. Just give me one minute. Taking out the question, you guys can't see it. Okay. Let's try to tackle part A. So, in part A, we're asked to figure out how much sugar will be dissolved in 1,500 grams of water at 90 degrees Celsius. So, if we follow the graph, so if we look here at 90 degrees, we'll draw it here. Okay. So from figure 1 at 90 degrees, if we follow that over and down to the weight percentage, based on the problem, they're saying that's about 77%. So you may, for homework, have to kind of guess that value a little bit when you guys do problems, based on where your temperature and your weight composition meet up. So here they're saying it should be about 77 weight percent, and now that we know the weight percentage, now we can calculate the mass of the sugar by using this equation here. And so we'll say 77 is equal to the mass of the sugar, which is what we want, divided by the mass of the sugar again, plus the 1,500 grams, which is the mass of the water that we know that we have, multiplied by 100. And so if you manipulate the equation and you start moving your variables around, you'll just find that your mass of the sugar should be equal to about 5,022 grams, which I don't know how they do that. That's a lot of sugar. Okay, and then so for part B, we're going to be kind of doing like a similar process. So using the same plot, we're going to, so at 20 degrees, let's do this. So at 20 degrees, this is where I hit my solubility limit. And I'm going to go down to find the composition or weight percent. And according to this problem, that should be about 64 weight percent. So at 20 degrees, the solubility limit or the concentration of the saturated solution is again should be this amount here. So pretty simple. So you just go to your 20 degrees Celsius, you track over until you hit this guy here, the solubility limit, the red line, and then you make your way down. I would say the hard part is determining correctly what value this is, and it's also important to note that I'm looking at the sugar here and not the water. I believe they also mentioned that as well in the question. They want to know what the weight percentages of the sugar. And for part C, we're trying to do that over here. Hopefully I don't cut off too much of the problem. So in part C, they want to know how much of the solid sugar will come out of the solution upon cooling to 20 degrees Celsius. So the mass of the sugar, since we know from part B that the weight percentage is 64 weight percent, we can now calculate the mass of it at room temperature, which I'll go ahead and do that now. So we're going to have 64, which is equal to, we're going to call it M prime this time because we kind of used N by itself. So we don't want to confuse the different calculations that we're doing. And multiply that by 100. And so if you solve for this to get the mass of the sugar at room temperature, you should end up with 2,667 grams. But there's still one more step. So you have to subtract the original mass of the sugar that we found here in part A from this guy that we just found in order to get the amount of sugar that precipitated out of the solution as you were cooling it. And so we call this M prime, so we'll call this M double prime so we know what we're talking about. So this is where I should say the part C comes in for this question, where we're trying to figure out how much of the solid sugar is coming out of the solution as we cool it. And again, this is simply just the mass of the sugar that we found in part A minus M prime of the sugar which we found earlier in this part C. And it's you guys can see this part, it's just 5,022 grams minus 2,667, which should give you 235 or 2355, 2,355 grams. And there you go. Any questions on this one? So in the chapter, they give a lot of steps and a lot of like background help and stuff. But if you're like last week of the exam, you're trying to like figure it all out, that's not a good thing. Like chapter 9 is like super dense. As I was kind of showing it, it seemed pretty simple and straightforward. But definitely give yourself enough time to actually like review all this, so that when exam time comes, final exam, you guys aren't stuck on a question like this one. Okay, so I'll give you guys a few minutes to try this one, which is also about the solubility limit. So in this question, they want to know, at 700 degrees Celsius, they want to know what is the maximum solubility limit of copper in the silver. And I don't know why this printed out twice. So they want to know what the max solubility is of copper to silver, and of the silver into copper. So I'll give you guys a sec to work on that one. And again, because it's like 3:24 now, if we don't get through like all this stuff, we'll definitely go back to it next week Friday, and then we'll also try to squeeze in chapter 10 homework stuff as well, so that way you guys can do that. Go ahead and do this. I'll draw this line here. So I guess you can say the key for this question is paying attention to the composition of the weight percent. So this weight percent is in silver. So you need to pay attention to these guys here. So this is copper and this is silver here. So for part A, you have to look at here. So for copper in silver, they would need you to look at the beta phase, which is this guy here, and then kind of go down to figure out that weight percentage. Again, it's going to be a little weird trying to figure that out because they don't list anything in the examiner, so you got to kind of guess the limit. So this is 90. And the answer that they give for part A for that one is about 6 weight percent of copper. And for part B, we're going to be looking at the other side because we're going to know what the maximum solid weight of silver is in copper. So we'll go down here from this line. Again, this is about like 10. This kind of falls somewhere in the middle with between 0 and 10 weight percent. So this is going to be about 5 weight percent of silver. And for this one, it's important to remember that you have like 2 different metals going on here. So for example, if we look at part A again, this is in weight percent silver. It's from 0 to 100. So technically, all the way over here at this beta phase, if we look down, this is going to be, I believe if I were to guess, this should be about like 94 weight percent of silver. And so if you subtract that out of 100, you should get, if my math is right, I don't know if I'm mathing right now. You should get about 6 weight percent. So if 94% is silver, if you do that easy arithmetic, you should end up with about 6 weight percent of copper. Again, I don't know if that math is right, but that's kind of the idea. And then for part B, we're trying to figure out silver, max solid weight of silver into copper. So again, we're at our 700. In that case, for part B, we're taking a look at the alpha phase, or staying more to that alpha phase, and then going down. And then we're kind of reading basically wherever we fall here, which in this case is supposed to be 5 weight percent. So part B, you're kind of like, in part B, you're following the table kind of like how you see it, and then part A is kind of like the tricky part where you have to kind of like change your mindset a little bit and go all the way to the other side of the table, do that simple arithmetic that I was telling you guys about, and then from there you'll get the right answer. Any questions on this one? So not too bad. So it's 3:34 now, so let's move to, so this is again is another section like in your book, and it's titled Interpretation of Phase Diagrams. This is I guess the other section, I guess you could say, that's in your homework. And then to try and briefly explain what's going on here. So for a binary system of known composition and temperature at equilibrium, your text mentions that there's going to be like 3 different kinds of information that you can find, which are the phases that are present inside of the phase diagram, the composition of these phases, so like how much of one element is mixed into another basically, or if there's no mixture at all. And then the other thing that you will learn from it is the percentages or fractions of the phases. So to talk a little bit more about how to determine the phases present, I mean that's very easy to do. You just have to locate the temperature composition point on the diagram, and you just note the phases that correspond with that phase field that's labeled. So kind of like I see here, like, so say for example, we went to like 1500 and we wanted to know, or I should say, not this one. So it's like, say we go to like, I don't know, 1200. Okay, at 1200, we want to know what this phase is. This is going to be our liquid or liquidus phase. And we go on from here. Say for example, we want to figure out what the weight percent of nickel is if we go into this L plus alpha phase. We would then have to like go a little bit more inside, and that would take us to about like 38%, so on and so forth. So it's more sort of kind of just, you're just identifying it. And to speak more about the determining the phase compositions, so your first step would be to determine the phase compositions in terms of component concentrations, to locate the temperature composition point on the phase diagram. And there's different methods that are used for the single and two phase regions. And the one phase region is fairly simple. You just have the composition of the phase, which is simply the same as the overall composition of the alloy. In a two-phase region, it's a little more involved. So in all two-phase regions, in two-phase regions only, so you can imagine a series of like horizontal lines, one at every temperature. And that line, that imaginary line is what we call the tie line. So that's over here on this slide here. And sometimes they call it an isotherm, and that line, that tie line, extends across the two-phase region, and they'll terminate at the phase boundary lines on either side of it. And your book talks about computing the equilibrium concentrations of the two phases, and they give like a little like procedure list in your text. So I guess the first step in order to compute the equilibrium concentration of the two phases would be to create the tie line. So you create the tie line in the two-phase region at that temperature of the alloy, and then the intersections of that tie line and the phase boundaries on either side, you basically like take a note of them. So kind of like how they did this figure here. Here they wrote down 32 weight percent of that L phase, and then 43% of that alpha phase. And then the perpendiculars are dropped from these line intersections to the horizontal composition axis, which is basically what they're doing here with the dotted lines, from which the composition of each of the respective phases is read. So basically what they're doing here, just what they're doing with the dotted lines here, figure out that they have 32% of the L phase and 43% of the alpha phase. These are some of the equations here in these orange boxes of basically how to solve them or solve for them. And I believe there should be another slide. Yeah, so in the next slide too, those equations are basically lovable. So I can quickly go over that. And that takes us into, I guess, the third point that the text was trying to talk about, which was determining the phase amounts. So the relative amounts as a fraction or as a percentage of the phases present at equilibrium may also be computed with using the phase diagram. And again, the single and the two-phase situations are going to be treated differently. So the solution for the single-phase region is going to be just straightforward. Because only one phase is present, the alloy is going to be composed entirely of that one phase. for the two-phase, it's a little more involved, but the book does a good job of giving steps to figuring that out. So, if the composition and temperature position is located within the two-phase region, again, we're gonna use the tie line thing that we learned about in that last slide. And the first step we're gonna do is create the tie line across the two-phase region at the alloy temperature. Your second step at that point then would be to basically determine the overall alloy composition located on the tie line. And then next you would look at the fraction of one phase by computing the length of the tie line from the overall alloy composition to the phase boundary for the other phase and divided by the total line length. After that, the fraction of the other phase is going to be determined the same. And then lastly, if you want the phase percentage, you just multiply each of the phase fractions by 100 and you can return it to a percentage. And they mentioned that you can directly measure those tie lines, I believe, in your phase diagram using a linear scale, but you can use the subtracted compositions as taken from the composition axis. So basically, they're just talking about these equations here, the WL and the W alpha. So if you don't have the other data, then you can just use this equation and you can do the arithmetic on those composition amounts. And so here you have the overall alloy composition is going to be your C naught, and your mass fraction is going to be represented as your W L and your W alpha for the respective phases. And so basically the sum of the because that was a lot. The lever rule is used to determine the relative amounts or fractions of the phases in any two-phase region of a binary alloy, provided that the temperature and composition are known and the equilibrium is established. And so it's already like 3:42, so let's go to this one. So I'll show you guys how to do this one quickly, and then we may not be able to get to the second question for you guys to try and run, but when we come back next week, we can just go back to the slide and try this one or yourselves. So one moment, and we'll go to solve this problem. Okay, so I should first read the question. So the question reads, there's a magnesium lead alloy of mass 5.5 kilograms, and it consists of a solid alpha phase that has a condition that is just slightly below the solubility limit at 2 degrees Celsius. And they want to know what the mass of the lead is in the alloy. And in part B, they want to know if the alloy is heated to 350, how much more lead may be dissolved in the alpha phase without exceeding the solubility limit of this phase. So we'll try to work that quickly and show you guys how to solve for this one. they mentioned, they give two temperatures, so I'll go ahead and just write those out. Oh, and also, I guess to repeat myself a little bit, so the figure here, this is that interactive figure that I was talking about. Super helpful if you want to practice these on your own. So at 200 degrees Celsius, here we hit that solubility limit, I believe they want us to hit. What is the mass of lead in this alloy? Yes, so I'm in the right spot. So here this is about 10 weight percent of lead. Yeah, so we're in the right spot. 10 weight percent of lead, so this is about 5 weight percent. So knowing this by looking at the phase diagram, so we go to 200 degrees Celsius. They want to know what the mass of the lead is in this alloy. The composition is in weight percent of lead. So we go to the 200, we travel over until we hit this solubility limit here, and then we go down, and that should be about at the halfway point. And then our next step is to then determine the mass of the lead. So in that part, I don't see where they mention equation, but essentially you know the composition weight percent, which is 5 weight percent, or if you write that out or convert that into, like, as you say, decimal form, that's just 0.05. And they tell you what the mass is in this part, which is 5.5 kilograms. So now if you solve this now by, so this is unitless, this is going to be mass, and so they want mass. So you would multiply these two values together in order to get your mass of the lead, which they mentioned is 0.28 kilograms. So that part, not super intuitive, but you just have to remember, since you know what your weight percentage is, and since the mass is given, you can find the mass of the lead within this alloy. And so that's basically what you would do to solve for the mass of the alloy, or solve for the mass of the lead. And then part B, so the solubility limits at 350, which is about this guy here. So we'll just draw a line out and then come down. And so the solubility limit of this alpha phase that we're in is about 25 weight percent. Again, you're gonna have to guess a little bit probably for your homework, or you'd use these little sliders. I think you'll have those available to you on your homework. And then to determine the additional amounts of the lead that we can add to this, we have to use, I believe we used this equation earlier, which is our weight percentage equation. So for part B, you'll have your composition of the lead, that's going to be equal to 25 weight percent. And in order to find out how much more lead we can dissolve in the alpha phase, we need to find, or we need to plug in these values here, so we need to find or plug in this value here, the mass of the lead that we found previously. Also, add to the mass of the lead that we want to add more of into this solution. And then we divide that by the total mass. I believe our 5.5 was the total mass of the magnesium lead alloy. And that is in kilograms. And again, that's added to the amount of mass that we can add of the lead. And this is multiplied by 100. And so solving for this, you'll end up with if you move around everything, your variables will not. You'll end up with a mass which is equal to about 1.46 kilograms. And again, I believe this equation is similar to the one that we saw in that last problem. This should just be one of your composition equations. Or like the weight percent equation, sorry. And I'll put a little box on this one. So, any question on this one? We're at time now, so. So if there's no questions, we'll pick up next time. We'll have you guys, we can do a quick review again on this section, and then I'll have you guys follow up and do this question. And then there's a couple more to go over, a couple more sections to go over, so that you guys can do your homework. And yeah, that's all I have for you guys. I guess final words on the exam. Just make sure you guys study your slides, go over your homework. There's definitely more practice questions in like the back of your chapter, so definitely do that as well, so you guys are ready. And also review some of your recitation slides as well. I think those are going to help out a lot with your exam stuff. So yeah, so that's all for me. We'll see you guys next week. Well, for the exam and also recitation.